Okay, so now we can move on to the current laws. We know externally applied E field creates current densities in conductors. And now we know how to formulate them. J equals sigma E. So once you know the material's conductivity, you know the current density. How can that really help us? Well, once we know J and E, how they're related, we have already derived Ohm's law, V equals IR. And then we can also understand other things, right? KVL, Kirchhoff's voltage law, Kirchhoff's current law. Everything can be understood. And as I promised, if you still remember, in the previous chapter, up front, when we talked about metals, I told you perfect metals cannot have charges inside of it. But if you forcefully inject charges into the metals, the charges will swim to the surface in a very short time. And now is the right moment to prove that statement is true. So we are going to talk about charge dynamics in conductors. Now that we have the basic understanding of conductivity, finally, we have the ability to understand it. All right, again, just to recap what we covered in the previous subsection, J equals sigma E. So sigma is the conductivity for that conductor. Still, E fields are conserved. So that means you cannot violate curl of E equals to 0, right? E fields, by default, are conserved, so the curl of the E field intensity must be 0, right? And whenever you see this curl equation, curl is related to finding the circulation in a closed loop. So that is transformed. You form a closed loop and you evaluate the resulting closed loop integration of the E field intensity. And that has to be 0. Otherwise, you're working in a non-conserved field. So we can simply replace E by J divided by sigma, right? This is coming from the fact J equals sigma E. So this formula tells us, well, somehow, current density, well, divided by sigma. Sigma is a constant. We can just pull it out of the line integration, right? So this formula is telling you, well, current density is also a conserved field, right? Now think about it. Does it make physical sense? I mean, this one makes physical sense, right? In the world that we live in, E fields are conserved. But somehow J equals sigma E, so if this is conserved and that's a constant, it's making J also conserved, which is too true. It cannot be wrong. And therefore, you see this equation, you accept it. But this is a point where you really have to ask yourselves and cast doubts. How to form steady state electric current in the first place? What do I mean by that? Well, let's take a closer look. So imagine in space you have a positive charge, right, moving with certain velocity, and that gives rise to J. Okay? Now, the entire chapter assumes you have a constant and steady flow of charges at a given velocity, right? Therefore, you have J. So if you have some kind of circuitry, well, some kind of circuitry, okay? This is some circuitry, right? We want to form a closed loop. So you might have two resistors connected in series. So think about it. If this is true, J, we can skip sigma, right? Assume sigma is 1. So J dot differential length, we form a closed loop, has to be 0. So let's check. We formed a closed loop called C, right? And the closed loop direction for the top segment from the left to the right, and then it goes down, reverses direction, and also reverses direction in the y direction. Okay? So that is my closed loop C. On the top segment, I have assumed the positive charged particle moves from the left to the right. So my J is moving from the left to the right. Okay? So once the charge moves to here, to this corner, how should it move? I mean, it's simple, right? It's just, so my current is moving from the left to the right, and once I hit this corner, it has to change direction. It has to bend by 90 degrees, right? When it reaches to here, current density, or the flow of the charge, keeps on going, right? And then when it meets this corner, goes up, right? This is how you maintain a steady state current, right? So this charge moves across the resistor, goes down, moves here, and goes up. And therefore, you have a charged particle continuously moving in this loop, right? So this probably answers how we can maintain a steady flow of charged particles, right? We have to form a closed loop. Otherwise, the particles move, then after some time, you don't have any more particles, right? So once you form a closed loop, this one goes around and comes back here again, can move, right? So the total number of particles does not change, and therefore you have a steady flow of current. If you're smart and if you're sensitive, you can catch some bug in that statement. Now, you should be able to catch the bug. Because if we want to maintain a steady flow of current, it means this charge has to move with a constant velocity, right? But the fact I have resistance in my circuitry, that means when the charged particle is moving along the loop, it loses energy, right? When it loses energy, its velocity should be reduced, right? It's due to bumping, due to collision. Every time you bump, you lose a small portion of the energy into heat. So even though the number of particles can be maintained in this closed loop, but the velocity cannot be maintained at a fixed rate. Okay? So what is the problem? That's problem number one. The velocity cannot be maintained. And the second one, it seems to violate this universal truth. This equation tells you in my closed loop circuitry, the line integration of J should be 0. But let's check, okay? Let us check. Here, the top segment, J is in the same direction of my differential length. So this is giving me a positive sign, right? J and dl are in the same direction. So they multiply together, they're positive. It gives you a positive value. Here, again, the current is bended in the same direction as my differential length. So these two multiply together, again, gives me a positive value, right? Once I perform the integration. Here, same direction, positive. Same direction, positive. So you add 4 positive stuff. How can that be 0? This is my challenge to you. Draw a simple circuitry, and you assume to have a steady flow of current. Can you try to prove, or just try to convince me? How can this universal truth be held? It's actually problematic, right? We have 2 problems. Number 1 being, well, it seems like the closed loop integration is not equal to 0. And the second one is mu seems to be not a constant. Okay? Such a simple circuitry already violates 2 of our understandings. Okay? So the fact of this equation being so simple, you must be able to link the equation to reality. So the basic question, or the 2 problems, can be answered by asking ourselves one simple question. I mean, how can we maintain the circuitry to operate with a constant current? Any answer from the student? No? How many students are watching? 8. Well, anyone that understands about circuitry knows that in order to operate, right, a circuitry, there's no free lunch. If you want to generate current, you have to feed the circuitry, right? If you want your horse to work, you have to feed it grass, right? Okay. So that magical box is called the batteries or the sources, right? This is something you learned. So in the past, in this box, you have to provide battery in the form of voltage, or you can have the current source. Either way, right? Which means circuitries are not there for free. You have to donate energies to make it operate. And basically, a circuitry gives you functionality, but it always induces losses. Okay, it's fair. So what I want to emphasize is the batteries that you use every day are very weird elements. I mean, they are ideally producing non-conserved fields. Okay? What do I mean? Let's look at the inside of a battery. Okay? So a battery comes with a positive side and a negative side. It still has two conductors. And to our understanding, the positive sides attract positive charges. The negative side attracts negative charges. Okay? So therefore, usually when you have positive charge, you create the field direction pointing from the positive to the negative. Right? And therefore, if you have a positive charged particle, it tends to move in this direction, right? E. But look at the circuitry. Look at the circuitry. I'm using the shorter segment to denote negative, a longer one to denote positive. In the circuitry, if you want to maintain a constant current, you need to supply some kind of potential difference in order to make it work, right? But when the charged particles move along the three segment, it loses energy. But when it meets the battery, it actually moves in the direction from the negative side to the positive side. So the positive charge moves, finishing the circuitry, and goes inside the battery. It moves in a reversed direction as compared to our anticipation. In our anticipation, the positive charge moves in the direction from the positive electrode to the negative electrode. But when the particle moves into the battery, it actually moves or swims from the negative side to the positive side. And therefore making the battery itself a non-conserved element, right? So the way to appreciate Kirchhoff's voltage law, this is Kirchhoff's voltage law, right? The way to understand it is, well, in order to maintain the basic operation of a simple circuitry, you need to apply or supply a battery. So in all these circuit elements, you suffer from potential drops. You lose energy. But once the charged particle enters the battery, it is forced to move in the direction reversed to our understanding in order to combat the energy loss. So it gains energy. Right? So basically, when you move in this direction inside the battery, you have potential rise instead of potential drop. Right? So the basic function of this non-conserved field, right, is forcing the charged particle to move from the negative side to the positive side to give additional energy of the particle, and therefore to maintain the velocity of that charge. Right? So, in order to have a steady electric current, you need to have a non-conserved field element. So when you have a positive charged particle moving with some velocity, although it undergoes a lot of potential drops, but all those energy loss is recovered by this battery. So the number of the charge remains constant. The velocity of the charge remains constant throughout. Okay? Very simple operation, and you must know to operate a circuitry, you need to have sources. But you never thought the significance of those sources are actually providing a non-conserved field element. Okay? Otherwise, curl of J seems to be non-zero.